For decades, Mars has captured the human imagination like no other destination. It's the next frontier, the obvious step after the Moon, the planet where humanity will become a multi-world species. Elon Musk promises cities on Mars within our lifetimes. NASA plans crewed missions for the 2030s. Countless science fiction stories depict thriving Martian colonies. But Michio Kaku, one of the world's leading theoretical physicists and futurists, has a message that contradicts all this optimism. Getting humans to Mars, he argues, might be impossible. Not impossible in the sense that it violates the laws of physics, but impossible in every practical sense that matters. The challenges are so numerous, so severe, and so fundamental that we may never overcome them with current or foreseeable technology. And the more we learn about Mars and the realities of deep space travel, the more impossible the dream appears. This isn't pessimism for its own sake. Kaku has spent his career analyzing technological trajectories and scientific possibilities. He's generally optimistic about humanity's future and supportive of space exploration, but he's also brutally honest about the obstacles we face. And when it comes to Mars, the obstacles aren't just engineering problems waiting for clever solutions. They're fundamental barriers rooted in biology, physics, economics, and human psychology. Understanding why Mars might be impossible requires looking at each of these barriers in detail. Start with the most basic problem, the distance. Mars isn't just far away. It's incomprehensibly far away in human terms. The Moon, which we reached in the 1960s, is about 240,000 miles from Earth. That's a 3-day journey with Apollo-era technology. Mars, at its closest approach to Earth, is about 34 million miles away. At its farthest, it's over 250 million miles distant. Even at closest approach, the journey takes 6 to 9 months with current propulsion technology. That doesn't sound impossible until you consider what it means. 9 months in a cramped spacecraft with recycled air, recycled water, constant radiation exposure, zero gravity, no possibility of resupply or rescue, and no way to turn back if something goes wrong. The Apollo missions to the Moon lasted days. The International Space Station supports astronauts for months, but they're only 250 miles up, a rescue mission away, with regular resupply ships bringing fresh food, water, equipment, and the psychological comfort of being close to home. A Mars mission would be different by orders of magnitude. Once the spacecraft leaves Earth orbit and begins the journey, the crew is committed. There's no abort option. If life support fails, if someone gets seriously ill, if a solar flare damages systems, if psychological problems emerge, there's nothing that can be done. The crew is on their own for the better part of a year just getting there, then however long they spend on Mars, then another 6 to 9 months returning. We're talking about a minimum 2-year mission, possibly 3 years depending on orbital mechanics. Kaku points out that we've never kept humans in deep space for that long. The longest single space mission was 437 days on the Mir space station, and that astronaut returned with serious medical problems: bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems, immune system dysfunction. And that was in low Earth orbit, where Earth's magnetic field still provides some radiation protection and psychological comfort of seeing home out the window. The radiation problem alone might be insurmountable. Earth's magnetic field and atmosphere protect us from cosmic radiation and solar particles. In space, there's no protection. The International Space Station orbits within Earth's magnetosphere, so astronauts receive only moderate radiation exposure. But beyond low Earth orbit in deep space, radiation levels are orders of magnitude higher. Cosmic rays, high-energy particles from exploding stars and other cosmic events, constantly bombard spacecraft. These particles can pass right through metal hulls and human bodies, damaging DNA, increasing cancer risk, and causing acute radiation sickness during solar storms. Solar particle events, sudden bursts of radiation from the sun, can deliver lethal doses in hours. There's no warning system that would give astronauts time to shelter adequately. Shielding against radiation requires mass, thick layers of material to absorb particles, but every kilogram of shielding is a kilogram that must be launched from Earth at enormous cost. Making spacecraft heavy enough to truly protect against radiation makes them prohibitively expensive to launch. Water and food stores could provide some shielding, but not enough. Some proposals suggest surrounding crew quarters with water tanks, but this only partially addresses the problem and adds tremendous weight. The trade-off is brutal. Light spacecraft are affordable to launch, but offer little radiation protection. Heavy shielded spacecraft would protect the crew, but cost so much to launch that the mission becomes economically infeasible. Kaku argues this might be a fundamental barrier. We can't make spacecraft both safe and affordable with chemical rockets, and we don't have any other propulsion system ready for human missions. Nuclear propulsion could potentially reduce travel time, shortening radiation exposure, and making the mission more feasible. But nuclear rockets are politically controversial, technically unproven for human missions, and would require decades of development. Even with nuclear propulsion, you're still looking at months in deep space with significant radiation risk. The medical challenges extend beyond radiation. Zero gravity for extended periods devastates the human body in ways we're still discovering. Bones lose density at about 1% per month in microgravity. After 9 months traveling to Mars, astronauts would lose roughly 9% of their bone mass. That's approaching osteoporosis levels, and that's before spending time on Mars, which has only 38% of Earth's gravity, not enough to prevent continued bone loss. Muscles atrophy without gravitational load. The heart, not needing to pump blood upward against gravity, weakens. Astronauts on the ISS exercise 2 hours daily to counteract these effects, and they still return weakened. On a Mars mission, that exercise equipment is mass that must be launched. And even with constant exercise, deterioration continues. The vision problems are particularly troubling. Many astronauts who spend months in space develop vision changes, some permanent. The mechanism isn't fully understood, but it appears that fluids shifting toward the head in zero gravity put pressure on the optic nerve and eyeball, causing structural changes. Some astronauts return needing glasses for the first time in their lives. Would this get worse on a multi-year mission? Could astronauts go blind? We don't know because we've never tried. The psychological challenges might be even more daunting than the physical ones. Humans didn't evolve for isolation and confinement. Antarctic research stations, submarines, and space stations have all documented psychological problems among crew members. Depression, anxiety, interpersonal conflict, and in extreme cases, psychotic breaks. And those environments have escape routes. Antarctic stations can be evacuated. Submarines can surface. Space stations can send astronauts home. A Mars crew would have no escape route for years. They'd be confined to a small spacecraft with the same handful of people, no privacy, recycled everything, constant danger, and the knowledge that any mistake could kill everyone. The Earth would be a bright dot in the sky. No larger than Venus appears from Earth. Everything they've ever known, everyone they've ever loved, is on that distant speck, unreachably far away. Kaku references studies showing that even carefully selected, extensively trained crews develop problems in isolated, confined environments. The Mars 500 experiment, where volunteers spent 520 days in a simulated spacecraft, revealed issues with sleep disruption, depression, and motivation decline. And that was on Earth in a simulator, where participants knew they could leave in an emergency. Real Mars missions would face worse psychological stress. Then there's the landing problem. The Martian atmosphere is about 1% as dense as Earth's. That's too thin for traditional parachutes to work well, but thick enough to generate dangerous heating during descent. Landing large payloads on Mars is extraordinarily difficult. The largest thing we've successfully landed is the Curiosity rover at 1 ton. A crewed mission would require landing dozens or hundreds of tons of equipment, habitat, life support, fuel for the return journey, and supplies. Every Mars landing mission has what NASA calls 7 minutes of terror. The descent phase, where the spacecraft enters the atmosphere at thousands of miles per hour and must slow down enough to land safely, all autonomously, because radio signals take 4 to 24 minutes to travel between Earth and Mars. There's no real-time control. The spacecraft is on its own, and the margin for error is razor thin. Scaling up from 1-ton rovers to multi-ton crewed landers multiplies the difficulty exponentially. Larger landers need bigger parachutes, which might not work in Mars's thin atmosphere. They need more retro-rockets, which consume more fuel, which makes them heavier, which requires more fuel in a vicious cycle. Some proposals suggest landing multiple smaller craft instead of one large one, but that increases complexity and points of failure. Once on the surface, assuming a successful landing, the crew faces an environment more hostile than Antarctica. Average temperature is -80 degrees Fahrenheit. It can drop to -195 degrees at the poles in winter. The atmosphere is 95% carbon dioxide, unbreathable, and so thin that liquid water cannot exist on the surface. It would either freeze or boil away depending on temperature. Dust storms on Mars can engulf the entire planet for months, blocking out the sun. Solar panels become useless. Equipment gets coated. Dust penetrates seals. The dust particles are sharp and chemically reactive, irritating to lungs and dangerous if inhaled, and these dust storms are unpredictable. A crew could land during calm weather and find themselves trapped in a global dust storm weeks later. The habitat would need to be completely self-sufficient, generating oxygen, purifying water, growing food, maintaining temperature and pressure, and doing all this reliably for years, with no possibility of repair parts from Earth. One critical failure, one seal breach, one air recycler malfunction means death for the entire crew. The complexity of the systems required is staggering, and complex systems fail. Kaku emphasizes that we've never built a closed-loop life support system that works reliably for years. Biosphere 2, an attempt to create a sealed ecosystem on Earth, failed within 2 years. Oxygen levels dropped, carbon dioxide built up, and they had to pump in air from outside. And that was on Earth with a large space, natural sunlight, and the option to open the doors if things went wrong. A Mars habitat would be smaller, dependent on artificial light for plants, and have no escape hatch. Food production on Mars presents enormous challenges. Plants need light, water, nutrients, and atmosphere. Martian regolith is toxic with perchlorates and lacks organic matter. It would need extensive processing before plants could grow in it. Water exists on Mars as ice, but extracting, melting, and purifying it requires energy. Growing enough food for a crew would require significant greenhouse space, lighting, and careful management. One crop failure could mean starvation. The psychological impact of living in a cramped habitat on a dead world for months or years would be severe. No trees, no animals, no weather except dust storms, no blue sky, no rain, no ocean, no variation. Just red rocks, pink sky, and the inside of the habitat. Some crew members might cope. Others might develop severe depression or other psychological problems, and there's no psychiatrist available, no way to evacuate someone having a mental health crisis. Then there's the return journey. The crew would need to launch from Mars, which has no launch facilities, no support infrastructure, no rescue capability if something goes wrong. They'd need to carry all the fuel for the return journey, or manufacture it on Mars from local resources, which requires bringing equipment to do that, which adds mass to the initial mission. The return journey faces all the same problems as the outbound journey: radiation, zero gravity, isolation, confined quarters, equipment reliability. But now the crew is physically weakened from months in reduced gravity on Mars. They're psychologically stressed from the entire ordeal. And they're using equipment that's been exposed to Martian dust, extreme temperatures, and radiation for months. The cost of all this is astronomical, literally and figuratively. Estimates for a crewed Mars mission range from hundreds of billions to $1 trillion. For comparison, the Apollo program cost about $280 billion in today's dollars, and that was for missions lasting days to a destination 3 days away. Mars is orders of magnitude more difficult and distant. Kaku argues that the economic case for Mars is non-existent. There are no resources on Mars worth the cost of retrieving them. No minerals, no elements, nothing that couldn't be obtained far more cheaply on Earth or from asteroids. There's no commercial reason to go to Mars. It's purely for prestige and exploration, which are wonderful motivations, but rarely sustain massive, expensive, dangerous projects over decades. The political will required to fund a Mars mission is also questionable. The Apollo program succeeded because of Cold War competition and a specific goal with a deadline. The Soviet Union was a rival, the moon was a finish line. We could plant a flag, come home and declare victory. Mars is different. There's no rival racing us there. There's no clear objective beyond land on Mars, and the mission would take so long, span so many political administrations, and cost so much that maintaining funding and focus seems unlikely. Even if one nation or organization started a Mars program, it would take 20 to 30 years of sustained effort and funding to complete. That requires political consensus lasting through multiple election cycles, economic downturns, competing priorities, and changing public interest. History suggests this is extremely difficult. The space shuttle was supposed to fly weekly and cut costs. It flew rarely and was enormously expensive. The ISS took decades longer and cost much more than planned. And those were low Earth orbit projects. Kaku also questions whether Mars is worth the risk. Suppose we commit the resources and accept the dangers. Suppose we develop the technology and launch a crew. Suppose they survive the journey, land successfully, spend time on Mars and attempt to return. If something goes catastrophic, if the crew dies, what have we gained? Is planting a flag on Mars worth potentially killing the crew? The scientific knowledge gained by crewed missions might not exceed what robots can learn at a fraction of the cost and risk. Robotic missions to Mars have been spectacularly successful. Rovers explore the surface. Helicopters fly in the thin atmosphere. Orbiters map the planet in detail. These robots don't need life support, don't suffer radiation damage or psychological stress, don't require food or water or return tickets. If they break, it's disappointing but not tragic, and they can go places and take risks that humans never could. The argument for human missions usually centers on flexibility and intuition. Humans can make decisions, adapt to circumstances, and explore creatively in ways robots cannot. But AI and robotics are advancing rapidly. Future robots might have enough autonomy to match human flexibility without the vulnerability. And humans can operate robots from Earth with some time delay, getting much of the benefit with none of the danger. Kaku suggests that the romance of Mars, the vision of humans walking on another planet, might be blinding us to the practical impossibilities. We want it to be possible so badly that we downplay the obstacles. Companies like SpaceX make optimistic claims about timelines and costs, but they're based on best-case scenarios, assuming everything works perfectly. In reality, aerospace projects routinely face delays, cost overruns, and technical problems. The space shuttle was supposed to make space routine and affordable. It did neither. The ISS was supposed to be a stepping stone to the Moon and Mars. We've been on the ISS for over 2 decades and aren't significantly closer to Mars. The James Webb Space Telescope was supposed to launch in 2007 for $1 billion. It launched in 2021 for $10 billion. If a space telescope sitting safely on Earth faces decade-long delays and 10-fold cost increases, what hope is there for a vastly more complex Mars mission? There's also the ethical question of what happens when, not if, things go wrong. A crewed Mars mission will almost certainly face life-threatening emergencies. Equipment will fail, people will get sick or injured, accidents will happen, and when they do, the crew will die, slowly, over hours or days, while the world watches helplessly. Is it ethical to send people on a mission with such high mortality risk? Is it ethical to stream their deaths for public consumption? Some argue that astronauts accept the risks and go willingly. That's true, but it doesn't resolve the ethical dilemma for the society that sends them. We'd be knowingly sending people to probable death for no compelling reason beyond exploration and prestige. Previous exploration on Earth at least offered the possibility of survival through skill and luck. A Mars mission that goes catastrophically wrong offers no survival possibility. You can't forage for food, hunt for water, or build shelter from local materials. There's no local environment capable of sustaining human life even briefly. Kaku also notes that we haven't even returned to the Moon in over 50 years, and the Moon is far easier than Mars. It's 3 days away instead of 9 months. We have experience landing there. The environment, while hostile, is less hostile than Mars. There's no dust storms. Solar panels work reliably. Communication delay is only a couple seconds. If we can't sustain a moon program, how can we possibly sustain a Mars program? The Artemis program aims to return to the moon in the coming years, but it's already facing delays and cost increases. And the moon is the easy part. If we struggle to go back somewhere we've already been with tested technology, what chance do we have of going somewhere new with untested technology facing far greater challenges? There's a psychological phenomenon in aerospace called Mars fever, where the excitement of the goal blinds people to the practical obstacles. Everyone wants Mars to be possible, so they assume it must be possible, and that assumption clouds judgment. Proposals gloss over problems, timelines are optimistic, cost estimates are lowballs and risks are downplayed. But wanting something doesn't make it achievable. Kaku doesn't say Mars is impossible forever. With radical new technologies, artificial gravity, fusion propulsion, advanced radiation shielding, closed-loop life support that actually works, AI capable of handling emergencies, it might become possible in the distant future. But with current or near-term technology, the obstacles are insurmountable, and the timelines being promised by space agencies and companies are fantasy. The harsh truth is that space is spectacularly hostile to human life. We evolved for Earth, for gravity and atmosphere and magnetic fields and ecosystems. Leaving Earth means leaving everything that makes survival easy. And Mars is far enough, hostile enough, and challenging enough that we might never overcome all the barriers simultaneously. Some might see this as pessimistic or defeatist. Kaku sees it as realistic. Acknowledging the true difficulty is necessary for making good decisions about where to invest resources and energy. Maybe the moon is achievable and valuable as a closer destination. Maybe orbital habitats make more sense than planetary surfaces. Maybe we should focus on robotic exploration for now and dream of human Mars missions for a future when technology has advanced sufficiently. The vision of humans on Mars is beautiful and inspiring, but inspiration isn't enough. Physics, biology, engineering, economics, and human psychology all have to align for the mission to work. And right now, they don't align. The distance is too far. The radiation is too severe. The life support is too unreliable. The costs are too high. The risks are too great. The timeline is too long. The political will is too fragile. The return on investment is too small. Mars might not be impossible in the absolute sense, but it might be impossible in every practical sense for the foreseeable future. And that's the message Michio Kaku delivers, not to crush dreams, but to inject realism into the conversation. If we're honest about the obstacles, we can make better decisions about humanity's future in space. And maybe, just maybe, that honesty will drive the innovation and development needed to eventually, someday, make Mars possible after all. But that day isn't coming as soon as the optimists promise. It might not come at all.